Calculus was actually developed for the purpose of solving two particular problems. We're going to start with one of them, and that's finding the line that lays tangent to a curve. The other problem that calculus was really developed to find was to figure out the area of irregularly shaped items. It's called the quadrature problem. Find a quadrilateral whose area is equivalent to the given shape. But we're going to start with line tangent. The first thing I must emphasize to you, the place in which algebra and calculus differ. Algebra is a picture. We've taken a snapshot and you can see exactly what's going on. These are the things we know. These are the things we don't. Let's figure out the things we don't know. And nothing changes. Calculus is algebra moving. So things change as we try and understand what's going on. We want to understand the way in which curves curve. What makes a curve curvy? That's got to be one of the stupidest sounding questions I've heard all year. But it's a legitimate one. How do you define, how does it make sense to talk about how curvy something is? Future engineers, current drivers. How do you know how curvy a corner is when you go around it in your car? The big old sign tells me how fast I'm allowed to go, right? Don't go more than 50 miles an hour. The truck will tip over. Don't do that. It says that on a big yellow diamond on the side of the road, right? How'd they figure it out? You're in your car. Let's say you're in somebody else's car, so you're not driving. You're sitting in the passenger seat, and they make a right turn. Where do you end up?
One of the weeks off that you want to keep moving. So when you turn your body, wants to move with it. So you turn to like counteract the other way.
An object in motion stays in motion unless acted on by an outside force. An object at rest stays at rest unless acted on by an outside force. Newton's first law, the law of inertia. If my person driving makes a right turn and I'm in the passenger seat and I'm not paying attention, I end up in their lap. Well, when I had bench seats, I could literally end up in their lap. Now I have bucket seats, it's okay. And you feel yourself go to the outside because the car is going this way and you're not nailed to the car, so the car moves out from under you and you feel it. If you take a really sharp corner, you feel a lot of that. If you take a really gentle corner, you feel very little of that. So one might say that a long, wide corner is less curvy than that sharp corner. We'll actually later on in this course, much later on in this course, define curvature formally. And we'll be able to say and measure exactly how curvy it is. But back in Greek geometry, you would have some curve, and your friendly geometry person would go, I'm going to pick a point on this curve, say this one. And I want you to figure out how to build, because Greek geometry, no algebra involved, nothing but letters and point high school geometry. That's all I'm allowed to do. I got a straight edge and a compass and nothing else. I want you to draw a line that only touches this curve in a local area at this one point. Only touch the curve right here at P, nowhere else. That's what it means to lie tangent to our curve. I only touch at that spot. The idea is that when you go off on a tangent, you've departed from where you were. Okay, so I'm here, now I'm going to go off on a tangent and go away from this thing. I'm a horrible geometer, especially in the classical Greek sense, but I can ad-lib this. That crosses more than once. That crosses more than once. How about we try that one? Not bad. And my Greek friends would be going, great, how'd you know that was where it was? I use my eyes. Eyes are not good in geometry. I don't know if you remember your high school geometry class, but you had all those lovely 2-column proofs where you had to do all these references to Euclid and this theorem tells me I'm this. That's nasty. I don't want to do that. So if this is my tangent line, I will call it LT for tangent. I want to figure out how to get that line's equation if I know the equation of the curve. So let's change this problem and give some equations to go around here. We know that shape. What's that curve look like? That's my upward opening parabola, whose vertex is at the origin and who's got standard width. Let's pick a point on this parabola. I don't want to use 0. Let's use something else. Somebody give me an x value. 3. So if I'm on the point 3 something, what's the something? Okay. There's my point P. This is the graph y equals x squared. Back to Monday. If I want to draw a line, if I want the equation for a line, I need a slope, I need an intercept. To get those things, what do I need? Say that again. 2 points. I only have 1. Oh, hold that thought. I don't know what that means yet. I need another point. So I'm going to pick arbitrarily another point on my curve. Where do you want that point to be? To the left or to the right of P? We're going to do them both, but we need to make a choice to start with. Left or right? So if I'm going to the left of my point P, then my next point, I don't know, Q, be somewhere over here. So a point to the left of P. And what I'm going to do is I'm going to draw the line that goes through P and Q. I'm going to get the slope that goes through P and Q. The slope, M, of the line passing from P to Q. All right. Well, that's going to depend on what I pick for Q. Let's start with nice, easy numbers. Here are 2 different choices for Q. We'll start with the point 1, 1 and the point 2, 4. 1, 1, 2, 4. Yeah, I can even see where those would be on my graph. If I have the point 1, 1, then the slope from P to Q, change in y over change in x. Change in y over change in x. Now, unfortunately, that's the line that goes from this point to P. That's clearly not a tangent line. It goes through the graph more than once. It's okay, we'll make it better. If I go from 2, 4 to 3, 9, then my slope is three minus 2. And I get a slope of 5. With me so far? Let's actually draw both of these lines back on our picture. And let's see what we can talk about them a bit. So I slide back up here to my picture, lay down my ruler, go from 3, 9 to 1, 1, go from 3, 9 to 2, 4. Here are my two different lines. This one was line 1, this one was line 2. Neither of these are tangent lines. But I brought the point Q closer to the point P. And by doing so, the part of the graph that I cut off with my line got smaller. Again, I don't come up with these terms, but the Latin word for cutting is secare. So we're going to call these secant lines, because they cut off a piece of the graph. And as I got closer, as I moved Q, moving, algebra in motion, I want to keep moving things. As I got Q to be closer to P, my secant bit got smaller. Let's get closer still. If I'm at an x value of 2.5, what's my y value? You all own a calculator. You do not have to do this arithmetic in your head. 2.5 squared is 6.25. So my slope is, well, 9 minus 6.25, change in y. 3 minus 2.5, change in x. 9 minus 6.25 is 2.75. Divide that by 0.5 and we get, say it again, 5.5. I'm closer. Okay. Do it again. Let's get closer still. Over and over and over. I'm going to continue to get closer. 2.9 for an x. 2.99 for an x. I need y values. I need slopes. 2.9 squared. So my slope, 9 minus 8.41 over 3 minus 2.9 is 0.59 over 0.99. 1, which gives me 5.9. When I repeat this, I get a slope of 5.99. What do you think is going to happen as I add more nines over here? My x value. I should add more nines here, right? So I think I'm going to get closer to 6. We've only looked at one side of this game. We only looked at what happened as Q came in on this side. What happens if I pick x values for Q that are bigger than 3? Maybe I'll get something different. Maybe I'll get the same thing. I don't know. We should check. Take your time. Find the y values, go with 3.5, 3.1, and 3.01, and the slopes that correspond to all 4 of those choices of Q. You got time. I noticed a lot of you repeatedly typing in your calculators. I want to show you a couple of cute tricks here. Here's my calculator. I'm going to go into the y equals menu and put in x squared. I can then hit the graph button. Here's my upward opening parabola. I can use the trace option, this button right here. And then I can put in whatever number I want, 3.5, 3.1, and it'll give me the y values. If I want to keep these hanging around, above window, it says TBL set, table setting, second table set. Right now, if you do that, I'm pretty sure on this line, your auto is highlighted. Yes? Go down to that, move over to where it says ask and hit the enter button. That'll change the highlight from auto to ask. Then when you go to the table, which is above the graph button, it'll be blank. And then you can type in whatever number you want in the X column, and it'll generate for you automatically the Y column. And if you move over, you can see all the extra decimal places down there at the bottom. It's above the graph button. It says second table. So you have to set it to be in ask mode, and then you go to the table. It's Miss Manners. We always set the table before we go to the table. So I now have all of the numbers I need here. And I can do my slope calculations. (16 minus 9 is 7. 4 minus 3 is 1. So I get 7 up there. This is 3.25 over 0.5, which is 6.5. Here I get 0.61 over 0.1, which is 6.1. And here I get 0.0601 over 0.01, which is 6.01. Hey, we're coming towards the same number, aren't we? I'm happy about this. I can now make an educated guess. As Q gets closer and closer to P, slope of our secant line gets closer and closer to 6. In geek speak, I'm going to use an arrow. As X gets closer and closer to 3, because that's how we figured out what our point Q was. We allowed the X value to close in. Slope of our secant line gets closer and closer to 6. If that's the case, I hope you are comfortable saying that the slope of the tangent line should be 6. Now, I want you to understand, the sentence I just said to you out loud took over 120 years to argue about. And those arguments go back 2,200 years. But are you comfortable with the idea of saying that the tangent line slope should be 6? I got a couple people nodding. Some of you are just staring at me like, what? Think about it. Are you okay? If I look at those points getting closer from above, we get a slope of 6. If I look at the point getting closer from the bottom, we get a slope of 6. I'm going to say if I'm only at that one spot, I should have a slope of 6. Maybe. No, because the graph itself is still fine. This line is not part of the graph. There is no asymptote going on here. The graph itself, y equals x squared. Y equals x squared is that parabola. We're over here at the spot on 3, 9. That's part of the graph. This line is a separate entity that only touches the graph at that one spot. Now that's actually a really weird statement. Oh, that's MT. Remember we had our tangent line, we called it LT. So I'm going to let M be the slope of that line, MT. My apologies. Why was there a huge argument about this? What did I do here that pissed off a lot of people philosophically? I made a what? I made an assumption. Well, I would say I drew a conclusion. But, I mean, I got to go all the way back to Greek philosophers. I'm sorry, I can't quite hear you from back there. And remember, Greek geometers were all about rigorous proof. They wanted formal, exact, anal retentive, pain in the neck proof. Guy by the name of Zeno. Greek philosopher by the name of Zeno. Z-E-N-O. Zeno was a real pain in the ass. I want to imagine an object flying through the air. It is launched at some time. It will land at some time. Let me make a nice, simple statement. The time it takes between takeoff and landing is 1. 1 what? 1 whatever. In order to get from the start to the end, first I have to get halfway there. That takes some time, doesn't it? So getting half the distance takes an amount of time. Getting the other half of the distance will take an amount of time. But let's look at that half. Getting half of that takes some time. Getting half of that takes some time. No, nothing about average. I'm going to look at my clock. From here to here, it took a certain amount of time, right? From here to here, it took a certain amount of time. From here to here, it took, wait a minute. If I asked you to take out your phone and take a picture of this flying through the air, what would you see on your phone screen? Would you see floating up there, right? Completely unattached to everything. Hung in midair, pinned to the ether. I'm not unhappy about that. But Zeno sure as hell was. Zeno's conclusion is that if I keep looking at smaller and smaller pieces of time, the object never moves. Ever. All motion is illusory and is simply the product of our mind attempting to interact with the behavior of the gods manipulating the world. What? Dude, I know you couldn't drink the water and drank a lot of wine as a result, but man, Zeno's wasted. I don't understand any of this guy. Zeno's paradox. This is how formal this got. This was routinely discussed. Zeno's paradox is that nothing can actually move because there are a certain number of sub-intervals that I have to think about, sub-pieces of time, and I would have infinitely many pieces of time to add up. And you can't add infinities. Think about the distance between P and Q. It's still there. No matter how small it is. Does P ever actually get to Q? They're two separate points. I put them right next to each other. They're not the same. Oh. So here's the philosophical question that we're really going to ignore for the most part. How do you do something infinitely many times and make it make sense? From the time Zeno came up with this argument, people would not come to a, and I'm going to put this in quotes here, satisfactory conclusion until the 1600s. And it would take another 200 years to really get the details down. The arguments we're going to cover in the next few days date back to the 1850s. The idea is 2,500 years old. So I'm going to tell Zeno to go pound salt. We're going to use this. It's going to 6. We'll figure out what that actually means. How do we do infinitely many things? Or something infinitely small in a couple of days. What if I pick a different point P? Somebody back there chose x equals 3. That's how we got 3, 9. For the record, that's not what's in my notes. My notes have the point 1, 1. Gosh, I got to do this whole thing again. If I want to know what's going on at a different point, I got to do this whole process again. I'm not, but 10th place, but I started at 3. Am I sure that those are all going to work out the same variation? Remember, my curve changes. It's a lot curvier at 1, 1 than it is out there at 3, 3, at 3, 9. The curve changes. What if I picked a different equation? Oh, crud. Well, now, when I'm at 3, I'm at 3, 9. But the tangent line's going to look different, isn't it? Because the curve is physically different up there. We can even look at the two different curves at the same time. Let me move in a little closer to what's going on at 9. Show me a little more room up there at the top. There's the x cubed minus 6x. Here's the x squared. Those two curves go in different directions. One of them is going like this, shallower. The other one's going like this, steeper. But they both cross at 3, 9. There's the spot. My little blinky there tells me that's the spot I want my tangent line for. I'm going to get a different tangent line with a different equation. Your fault, Zeno, and I don't like you because of this. All right. Wait a second. Let's stick with Zeno's idea for a minute. Zeno was talking about motion. Motion implies velocity. Velocity is distance traveled over time elapsed. An important statement. You can't just tell me where you started and tell me where you ended and how much time it took. You have to measure the actual distance covered. If you hit a home run, how far do you go? You better go 360 feet because it's 90 feet between bases. If you don't get the first, second, third, and home, you didn't hit a home run. You just stood there. But I started and ended at home plate. That's why it's distance traveled, not displacement. Physics geek terms. So, I live about 30 miles from school. I drive in the morning, it takes me 45 minutes. How fast am I going? About 40 miles an hour, because 45 minutes is 3/4 of an hour. So 30 miles in 3/4 of an hour is 40 miles per hour. I don't back out of my garage at 40 miles an hour. That would be difficult. I certainly don't do 40 miles an hour coming up the parkway. Or down Route 66. And I hope nobody's doing 40 miles an hour coming up the hill. Or through a lot. Not a good plan. You said this word earlier. What is this number? What is this speed? An average velocity. On the other hand, my car does work, so I have a speedometer in my car. I look at my speedometer as I'm coming up the hill, I'm doing 17 miles an hour. I have a speedometer as I'm going down 22, I'm doing 53 miles an hour. I'm on the parkway, I'm doing 67. I don't want to run over by the truck behind me. Those are not average velocities. Now, technically, I am kind of abusing the word velocity here because I don't tell you what direction I'm going, just how fast I'm going. I should be using the word speed, but I'll let that be flexible. Velocity is a vector. My physics people will yell at me. Instantaneous. Wait a minute. Velocity is distance traveled over time elapsed. What do you mean by instantaneous?
I was saying they're not moving at all, but it's not being kind of instantaneous velocity at that moment. It's how much that thing's going at that moment.
Okay, so now I'm going to really tell Zeno to go pound salt. Think about this for a second. When you took that picture and this sucker's just hanging there in the air, hidden in that moment is something you can't see. That this would be moving if you unfroze time. Because your snapshot froze it. So there's an instant there where time's not moving. And this still has motion hiding in it. Newton said the quantity we are looking at is fluid. It changes. And so he called it a fluent. So the spot where this is, that's the fluent. But it contains in it something that is changing, something that is in flux. So a fluent has a fluxion to go with it. At an instant in time where we see nothing moving, motion is still present. How? Gravity, right? Newton's British, we'll use the metric system. An object falling covers a distance of 4.9 times t squared meters in t seconds. Okay. Instead of dropping it here on the table, I throw it out the window. It still falls at that rate. Between 1 second and 2 seconds. Like I said, as long as it doesn't disturb the rest of it, take the call. Between 1 second and 2 seconds. Where are we at 1 second? When t equals 1, how far have we gone? When t equals 2, we're at and those are distances in meters. We'd move down 5 meters, 4.9 meters, and then 19.6 meters. That means between times 1 and 2, the velocity from time 1 to time 2. Hey, look, it's an interval. I'm going to take an average over that interval. I'll write that interval as a subscript so I can keep track of it. Some people will write the average with a bar over it. Like we have X bar for mean in statistics, that bar meaning average. I know at least one textbook that writes AV down there for average, but we're going to talk about the average between times 1 and 2. Well, that's change in distance, change in position over change in time. Somebody give me a number. I meant the number for this. Say again? And that would be meters per second. Change in distance, change in time, change in meters, change in seconds. Great. I can do the exact same thing that we did with our points P and Q. Do you want to know how fast this object is going at time 1 or at time 2? I want to pick one of those as my moment in time, the one I'm going to leave fixed, my P value. Let's use 1. Please notice that the sequence of calculations we are going to carry out are all going to look just like this. They're all going to look like that change in distance over change in time. Change in y over change in x. It's the same damn thing. Yeah, well, yeah, I can do it for any point. I'm just going to let t get closer and closer to 1, right? So I could do 1.5, 1.1, 1.01, 1.001. I could do 0.5, 0.9, 0.99. I can come in from both directions, just like we did, letting q come in from the left or the right to our 0.39. We let our x values get closer and closer to 3. I'm going to end up with the same idea. I need a position value. I need S of 1.5, 1.1, 1.01. Let's go to town. When I compute those S of 1.5, S of 1.1, when I compute those S values, they're going to go here in our change in distance part. So I put in the equation 4.9t squared, well, 4.9x squared into my calculator, and I can go through and get those numbers off the table. And I'm a geek, I'm going to keep all the decimal places here. again, I think I can start making an assumption about what I think is going to happen as our time value gets closer and closer to 1. We should see this number here, this slope, this instantaneous velocity, close in on the number 9.8. I hope. But I did this all with t-values that were bigger than 1. We should do it again with t-values that are less than 1, make sure we get the same thing from both directions. So let's run this one more time. How am I getting these numbers? Okay. I'm going to take the equation 4.9x squared with the calculator. And all I'm going to do is plug these numbers in and read off the y values that go with it. So I hit the trace button and I put in 0.5. All I'm doing is plugging that number into this equation and churning out my y value. That's the position at half a second, 9/10 of a second, 0.99 and 0.999 seconds, respectively. Now, I will freely admit, I cheated. I set up the table and then went in and plugged in the numbers there. And I can read those numbers off here. And then I ran the answers through the calculator. Better? Right. More questions. Ask me more stuff, people. Yes, ma'am. Literally, all I hit was the y equals button. You've got something completely different there. Oh. This may be an older student calculator. Okay. Look up the top. You see how my plots are all turned off? You have plot 1 highlighted. At some point, you were doing something in statistics or something else, and you had to plot some numbers. So if you go up and hit enter, it'll turn that from being highlighted to being unhighlighted. And then when you hit graph, you should get this picture. Oh, okay. So hit the trace button. And rather than using the arrows to move, type in the number 0.5. Literally, just type it right on the screen. It'll let you enter an X value. If you get to the point you can't actually type a number on this screen, then you can hit second trace. Second trace brings you to the calculation menu, which will tell you the things the calculator can do. And notice that that first one there says value. If you hit enter on that, it'll give you X equals blank, and then you put in any X value you want. On our Canvas page, calculus. On our Canvas page, please load the Canvas page. Down here in my reference files pile, in addition to those handouts on the conic sections and the trig formulas, is this document says using a graphing calculator.doc. When I was at the University of Pittsburgh, one of the courses I taught was an algebra course there, and I had a teaching assistant by the name of Lindsay, and she decided she was going to write up instructions on using a graphing calculator. That's her document from 2000. It still works perfectly. It's not that long, and most of the things we're going to do in this course and in a stats course are in there. You were asking me about other programs? X8XP, that's a calculator program. So at some point, I'm going to want you to do that. That's back in chapter 4. Not worry about that right now. More questions? Well, at the moment, I'm taking them all because I want to be as precise as I can, but then it's going to depend on the situation. How many decimal places do I need? We'll actually talk about that specific question in general. If you are doing a problem about money, how many decimal places do you need? Everybody's going to say 2. I have a problem. I was doing a bond issue in my financial math class this morning. The bond issue was for $9.2 billion. I needed 8 decimal places. The city of Pittsburgh is about to try and release a bond valuation of a little more than $3.5 million to raise money for the city of Pittsburgh to do PAT transit, bus repairs and upgrades and such. They're going to float a bond. They're going to ask people to invest to the city to the tune of about $3 million. Maybe it was 13. I don't remember anymore. Big numbers. I need more decimal places. So it's going to depend on what I actually need. For the moment, I wanted them all just to keep track. We'll look at more specific question. Yes. Yes, I provided that, stole it right out of the physics books. Those are the times we are looking between. So this is the average velocity starting at 0.5 seconds and ending at 1 second. So we had the position at 0.5, the position at 1, and the time 0.5 and 1. Right, that's our change in time. That's our interval, the little piece of time we were using to measure between. There was another hand. Yes, ma'am. I sure hope there'll be an easier way to do this because this is a pain in the neck, isn't it? And this is the problem that we run into. And that's why I'm doing this way at the beginning, so you can understand that this applies to a lot of different situations. Once I can say all of these things are really asking me the same question, I can then say, what's the one way to do this and generalize. But I want to start. And that's why when we look at the assignment for this section, I'm just going to pull up chapter 2, section 1 real quick here. This first exercise, problem 1 here, is about a tank holding 1,000 gallons of water, which is draining. At 15 minutes, there's 250 gallons of water left in the tank. How fast is water leaving the tank at that point in time? A pebble falls off the side of a bridge. There's its height. A rock thrown upward on the surface of planet Mars. Dude. Okay. A smartwatch keeping track of your steps. What's your exercise? Are you in your zone minutes right now? I have no idea. A particle moving back and forth across a straight line. Position of a motorcyclist after accelerating. If, please let this work. If all of these ideas turn out to be looking at the same thing, then I really only have to have one method for doing this. That's a big if, isn't it? There was another hand.
So, in the other book, the ones that we did before for the velocity pump, we kind of like flipped them around for like the bigger numbers first.
Yes.
But here,
right, and it was literally whichever one I thought. I put the minus 4.9 at the end. That just means that the top value here is going to be a negative number, right? But so is the bottom. 0.5 minus 1 is negative. So negative over negative is still going to give me a positive answer. Nope. As long as you're consistent. The order of the top has to match the order of the bottom, like we did with our slope. Change in y over change in x was y2 minus y1 over x2 minus x1. I didn't care which one was number 2s. Didn't care which ones were number 1s, but I had to use the same ones. I had to use the related pair, x and y, in each case. Better? Move. Yes, sir. Because I started to write it with that, and then I started to scratch it out, and I realized it wasn't going to make a difference because it was already a horizontal line. That dash over that shouldn't be there. And I hadn't dug out my liquid paper because I'm writing in pen. There, we'll white it out. Boop. That takes forever to dry, and I'll smear it on my hand or something, so we'll get there. More questions? Yes, ma'am. Yes, all of these should have units. They should all be in meters per second in this case. At the moment, we're keeping all of them. But hopefully the problem will say something about that. Last 2 years ago, the course I was using had a table and all the values were to 6 decimal places. One of my statistics courses, all of the table values are 4 decimal places. So we're stuck with whatever they give us. In a lot of cases, this is a matter for the lab science people. If you're taking chemistry, physics, biology, whatever, you're going to talk about significant figures. All numbers are significant here. I'm a math geek. I want exact answers. Let's go as far as we can. But you really can't get that much more precise than that much more, many more decimal places than what you were given. So if you were given stuff rounded to 3 decimals, then you should answer in 3 decimals. But in the interim, you should keep them all and only worry about significance when you present that final answer. For the moment, I'm keeping these all because I want to point something out. There's something interesting here. But I'll get there in a minute. More questions before I jump. I need to know the y values for the numbers I don't already know. So I knew when time was 1, we were at a position of 4.9, right? So I need to know the other ones to make the other part of the fraction up there. The y value I know went with the x value I know. The y value I didn't know went with the x value I was given, right? So I had to find this one. Just like we did in the graph, we had to go and figure out what these y values were so that we could then do that same thing. I didn't know the y value that went with this time, so I had to find it. I think these answers are getting closer and closer to 9.8. How far away is that from 9.8? How far away is that from 9.8? 0.049. 0.0049. 0.0049. Wait a minute here. Not only is the secant part, the difference, the pieces that I cut off, smaller, but it's the same whether we're on the left side or the right side. What an amazing coincidence. There's got to be a reason behind that. And it has to do with the type of equation we're looking at. If I were to change equations, that wouldn't be true. So here's the problem. It's a nice coincidence, but there is a reason for it. We might not know what it is yet, but it's not always going to work like that. Patterns I find right now, I need to make sure actually generalize before I can say, this is something I want to do all the time. More questions. Tomorrow, I'm going to make this a little more formal, talk about this idea a little more geeky, and then we're going to figure out next week how we do this faster. I want you to do what I asked for, right? The homework is our homework is on the assigned problems list up here on Canvas, right? This third spot here on Canvas, that's the list of problems. The problems that are due next Friday, not tomorrow, next Friday. September 5th, sections 1 through 3. Oh yeah, no, this is the list is. The list is just that, it's just a list. I want you to give me these in paper. I'll grade them and give them back. So you can print this if you want, but that's the entire list. That's what we're going to do all semester.
And then,
I only need these.
okay.
You can do all of these. You should do the odd problems in the back of the book because the answers are there. Then you can use them, make sure you've got your together, then do the even problems. If you came in late, please come sign my sign-in sheet. Turn